My name is Ilya Simonov. I'm head of CROC Immersive Technologies. We are IT company. We produce virtual reality trainings for industrial enterprises. And today I'm gonna meet you and show you example of successful implementation virtual reality training to the business processes of chemical company, CORYS. So, and before I start, I wanted to meet you and introduce myself more personally and to start from my own story and to move forward to the content for about training solution. So, this nice picture that you can see now, I I could see every day when I was young because I was born in a small town close to Moscow region, and we had one of the largest enterprise chemical company, chemical plant in our town. And from this time, I experienced many time. I experienced industrial industrial experience. I had industrial experience, and first time I experienced safety training of evacuation from like area which close to this plant. And from this time, I understood how industrial trainings, safety trainings are important for the people who work on these facilities, because if something happened dangerous, so it will affect not only on the process of the company and plant, it can affect for all area which close to this plant. So let's go to real life, and I will start from the hero of this story. This company called CORYS. Uh, Actually, it's chemical company. They produce mineral fertilizers for all countries, Russia and other countries. So they have 4 branches, and these 4 branches are operated by 10,000 employees. So this production is quite specific because they produce their products all the time that cannot stop. All of these plants, they have continuous production, and if something stops, so they will lose money, they will lose their products, and so on and so on. So many problems can be faced when something stops and when something works wrong. And this is quite huge problem, and this is problem for administration of this company and engineers who operating these plants. So this unplanned downtimes can be the reasons of these unplanned downtimes can be different. Actually, we can analyze 4 reasons why this plant can stop. So first of all, of course, is dynamic equipment which works every day, 24 hours, and so we need to repair this equipment, dynamic equipment. We need to stop, we need to maintain, we need to repair. So second is, of course, materials, technology processes. So it can be poor quality of materials, and third and fourth reasons. So these reasons which we are focused on when we creating virtual reality trainings. Third reason is electrical electricity. So if electricity will disconnect the production line, so it can stop all the production. And fourth is human factor. So this is not absolutely automatically operated plants. So people are involved to this process of operation. And so, of course, the education of engineers, workers who operate the plants is really highlighted problem, and they have many challenges how to do it faster, how to do it efficiently, and so on and so on. But the idea is we need to teach all these 10,000 people, but who we need to focus on and to prepare them more in efficient way. So it can be a lot of trainings to be done for these plants, but we focused on the main one. Main one is electricians who operate uh, who operate power substations, and this is the most risky work in this plant, I would say. So let's go to the challenges we faced when we started to work with Oral Chem, and we were trying to solve their problems. First one is when we want to prepare people to work in real life, we need to do it on existing equipment, and the equipment is working 24 hours, 7 days a week. So it's almost impossible to prepare people to react on some emergency situations, to prepare them how to operate real equipment without stopping this equipment. So, and some trainings are impossible to provide while this equipment working. So the second problem is long adoption time, long onboarding. To become independent electrician, it takes almost 5 years of uh, internship, of education, and so on and so on. 5 years to become independent electrician who can do like independent work. And third one is for management. It's almost impossible to control the level of skills. For example, we have 20 workers who can be managed, who can be administrated. And these workers we can divide on like high experienced, high qualified workers who work more than 5 years, almost 10 years. And we have part of them who just came to the facility, to the plant. And we need to prepare them for independent work and to decrease number of errors, number of some problems then which they can face. So, of course, the solution is to teach people on real equipment, to simulate something, some training solution where we have real equipment, but to recreate this physical process is quite costly, and it's almost impossible to recreate a whole technology process. We can create some training solution for only one equipment, or I don't know, two or three, but it's almost impossible to simulate all the process of uh, working of engineers. So about scope of work we've done, we focused on only electrical power substations and on 20 electricians who operate the substations and 6 substations. So as I already said, to become independent worker, it takes almost 5 years of internship and like preparation for independent work. And they have only once a year planned downtime for 1 or 2 weeks where they need to repair, to maintain the equipment. But only this period of time, this slot, they can train people to work by hands, to do something that they cannot do during all the year. So this is the big problem for management, for people, because they feel fear of working with real equipment when they see electrical schemes, instructions, and so on and so on. It's quite okay, but when they go to real facility, so they feel quite dangerous. So let me explain you what is virtual reality training and how it works, what it contains. So first of all, we needed to create digital copy of the real equipment and real processes. This is how it looked like in real life, and this is how it looked like in 3D and virtual environment. So this is absolutely the same copy of the equipment that Oral Chem has in their substations. So Actually, this is not only like a 3D environment. This is training solution which contains equipment, virtual reality equipment, and powerful PCs. Software which contains 3D copy of the facility, and scenarios where we can start, for example, shutting down of the old bus station and to repair it, and then we can launch it again to the operation. So this solution contains all these parts. This is how it looks like when electrician works in these scenarios. Here, from the first view, what he sees when he puts on helmet, and he can do all the operation that he can do in real life. So it's absolutely immersive, and this is not only like clicking what to do next, what to do previous. So electrician, he must do it by his hands. So he do all the processes from the beginning to the end. So this is how it looks like from the graphic side, because the main point is to not to recreate the equipment how it is in real life. You can see all the details that we needed to digitalize using photogrammetry, using laser scanning. So it's almost the same copy of the equipment that they have in real life. The problem is that for new plants, for new refineries, they have already like new equipment. We can find a lot of drawings, a lot of, I don't know, even 3D models of this equipment. But this case we worked, it was equipment, I don't know, 40 years old. So it's almost impossible to find some documents for recreating this data. So that's why we used real equipment, and we did many photos, laser scanning, and now you can see the picture in the VR training as it is. So this training, when electrician goes through this training, his work every time is recorded, and after he's done, management can see what he did during this training. So, for example, he made some mistakes during this training, and it's really essential part to go back to see what he did, how he did, and what can be, what they need to work together, what problems can be faced there. So now I'm going to show you video how it works, and the most important is what the feedback from the users and from the management. So before we implement this solution to real life, I thought that VR, virtual reality technology, is quite complex to understand how it works, to start working with it, because virtual reality is close to gaming solutions, but people who work in dangerous facilities, they don't play games. So they operating real equipment and they have dangerous work. So, and now you can see what the feedback from these people and how they apply these simulations. So let's see.
Interview with a EuroCam representative. Ilya Alexandrovich, hello. Let's talk about the project background and try to understand the reasons behind simulator implementation decision. We faced the need for components and high-quality training for our employees. Unfortunately, our plant does not allow for employee training on the existing equipment during the year, since it is always energized because of a continuous production process. Such training is only possible when the plant is stopped for scheduled repairs, which is very rare, once a year or once every 2 years. Since employees cannot be trained on the running equipment, gaining hands-on skills may take years. The use of VR simulator will help us dramatically accelerate the process. Please describe current personnel training process. Now, before an employee is permitted to make important critical switching, He must work as an electrician for 2-3 years and take an internship under the guidance of an experienced mentor. Only then he will be permitted to perform some actions independently. Hands-on skills can only be practiced once a year or once every 2 years, which is hardly acceptable since true mastering requires a long internship, continuous training, and repeated performance of the same sequence of activities. Let's talk about the use of the virtual simulator. Routine switching program has 2 basic scenarios: shutdown of the RP15 bus first section for repair and bringing it into operation. How many employees will be trained on the virtual simulator and how frequently? We plan to train 15 to 20 people on the VR simulator every year. These are mainly those who must know and maintain substantial equipment. The simulator helps employee get ready for the profession of a shift electrician without visiting a substation. A picture is good and helps to master skills. When operating a running system, an employee will know what to do and will no longer be so scared. The simulator can record training and testing sessions, generate reports, and export training statistics. What are the key features you will consider when determining whether a specialist is ready for the safe work performance? I would like to see that an employee not only performs certain operations with high quality and competence, but also his development progress, such as error rate and error severity reduction, so that there are no critical errors or faults. What main business benefits do you expect to get from the virtual simulator following the pilot operation? First of all, we want to reduce switching operation error rate and enhance reliability of the power supply of the entire enterprise. You're just starting to use the simulator, and the business effect is not yet known. However, you have already tried the solution during the acceptance test and obtained a result. Does it meet your expectations? Yes, it does. We have done a lot of work to create the simulator, and we hope it will help us a lot in personnel training. Numerous factors should be considered to create a true simulator rather than just a nice VR picture. What your industry peers who are new to VR should note to avoid mistakes and get a high-quality training solution. VR simulator developer should have expertise in Russian energy domain and understand what we want and how to achieve this. I would highly recommend you to pay attention to the personnel's feedback. Your expectations should be in accordance with their opinion, as evidently they are the vital resource that's going to bring your project to life. That is, how effective and how useful it will be for the employee who makes switching operations and will rely upon the knowledge gained from this program.
As you could see on the video, if you go to the link, you can see how it works and what the feedback. So in the end, solution work like this. So there is virtual reality equipment and software part. Virtual reality equipment quite simple. It's head-mounted display with plus joysticks and powerful PC that can run this virtual reality simulation. So it packs to the box and it looks like this. So it's it's almost plug-and-play solution where we can bring it to training center. We can bring it to, I don't know, a room close to operational room where electricians can do this training during their like daily routine operation. And so I would love to go back to the challenges again and to explain how it works now and how it affects on business processes. So training is impossible on existing equipment. Now training is possible without touching real equipment. So, of course, this is not only one solution that can educate our people, electricians to work, but this is the way how they can train their skills, how they can prepare during all the year, not to wait for one plant downtime a year. So, long adoption time. This solution is provided to the plant, but it also can be used in universities, in training centers who prepare people to the plant, to work on the plant. So they can start training before they go to the plant, when they educating and when they studying at the university. So, and impossible to control levels of skills. Management, uh, head of uh, mm, head of this bus station, power station, he get every time he get notification when engineer has done the training, and also he has video of how this training was done. He can see it if there is some highlighted points, for example, some errors that electricians faced. So and he can go back and to see this video and to make some decisions. And comparing to physical training solution to VR training solution, it absolutely different from the budget perspective. Now, for example, we need to scale this project to the another power substations. We need to change software. We don't need to change equipment. We need to change software. And now it's quite easy comparing to create again physical equipment for this equipment which quite old. So from the budget perspective, it's quite great. Um, but our idea is not to provide only like PEC as a solution, or our idea is to solve the issues and solve these challenges. And how we do it now. After we provide the solution, now every time, every half a year, we measure the results and feedback from the final users. So how they work, is it comfortable or not? So how many mistakes they do, and what are the mistakes? So we analyze the feedback from the final user, and so we measure all these metrics, and after that we can say efficient this solution or not. So this is what we are working on after we implement the solution. So this is it about this success story. You can find my contacts here. Thank you for your attention. And in the end, I would love to invite you to our booth. We have booth where you can find many videos, many presentations, and also I will be there with my colleagues. We can discuss everything if you are interested in implementation this kind of solution to your processes. So thank you very much. It was nice to share my knowledge. See you on our booth. Thank you.
Hi everyone, my name is Sarah Grace Mitchell and I'm the sales manager with CORYS. I'm excited to speak to you today about dynamic simulation, its use in the energy and chemicals industries, and talk about the qualities that make a good simulator. Following my brief presentation, you're going to hear from one of our engineers, Mr. Suhas Kulkarni, who will give you an in-depth demo of one of our models. At CORYS, we offer a wide range of solutions based on simulation. Our primary offering is high-fidelity custom models of your facility, which act as a digital twin and can be used for troubleshooting and procedure validation. We are DCS independent, and our software is compatible with all major DCS systems. In addition to custom models, we also provide lower capital cost standard models, which are available in the cloud with multiple different HMIs. These are great for training and operator fundamentals. Alongside our models, we offer custom training solutions, such as our companion training manual, as well as train the trainer services. Additionally, our engineers can provide their knowledge via consulting through dynamic engineering studies and what-if analysis. Now that we've briefly covered CORYS's offering, I'd like to make sure that we're all on the same page about what an operator training simulator is. So if you compare it to a plant has process units like an FCC or a distillation unit. There are field operators who are in the field opening and closing valves, starting and stopping pumps and more. And you have a DCS control system, and you have an SIS or ESD control system, and you have your DCS operator stations inside your control room. Now, if you look in the operator training simulator world, the process units are modeled in CORYS's Indus Plus dynamic simulation platform, which runs on a Windows desktop PC or a Windows server. We offer an optional field operator station where a field operator trainee can perform those field functions. This can also be incorporated into the instructor station. The DCS would be simulated by a DCS simulator, and the SIS is simulated by an SIS simulator. Then you would have your DCS operator trainee stations. The component that doesn't have an equivalent in the plant is the instructor station. And this is where the instructor will run the simulation, introduce malfunctions, activate training scenarios, and more, which we are going to see in just a minute in the demo. Though it's commonly associated with trainers and operators, the OTS can actually be used by everyone within your organization. Engineers can use custom models to streamline your process and test new control schemes. And operators, both new and experienced, use it to train on everyday procedures and more uncommon emergency conditions. Managers can utilize it to lower operating expenses, and HR enjoys its easy integration with your LMS and capture of best practices and knowledge transfer. CORYS owns a proprietary simulation platform called Indus Plus. It's high fidelity and extremely accurate in matching the actual plant performance. It can be used for DCS link or emulation. It also easily allows for linking to third-party software via the CAPE Open Interface standard, which allows for plug-and-play interoperability with third-party process modeling components such as compressor or reactor models. It also includes a trending and data historian, and it allows for using DCS graphics on the instructor station and field operator station HMIs. It also has some advanced functionality, which we're going to get into more in the demo. These are all of our standard models that we can provide. These are our standard refinery models that we can provide. We provide both component or small system models, as well as models of entire refinery units. These models are available in the cloud on a subscription basis with no software license fees. And please contact me if you'd like more information about these. With the subscription, we include setting up the selected models in the cloud and providing login credentials to the instructors and trainees. And we provide training sessions for the users and the instructors with additional support as needed. In terms of training materials, the models come with a user manual, which gets granular in the descriptions of the process unit and control scheme, as well as the simulator functions and startup procedures. Then we also provide a customized companion training manual, which is a classroom curriculum and description of the custom simulator training scenarios developed in coordination with your site's SMEs. Finally, as an option, we can consult on your overall training program and develop a training master plan to incorporate multiple simulation models into the curriculum, which is especially useful for the models that will be used for multiple sites. Now I'm going to turn this over to my colleague, Suhas Kulkarni, who is going to give you a demonstration of our simulator capabilities.
Hello everybody, I'm Suhas Kulkarni. I'm a lead engineer at CORYS. Today I'll be demonstrating the Indus Plus operator training simulator software. I'll be showing you the instructor station and the emulated DCS operator station. So I'll be going between the two views. So one screen will be the instructor station and the other one will be emulated DCS operator station. So let's get started. I'm going to first start the instructor station view. So there will be an icon like this on the instructor station in the OTS. So I double click on it. So the instructor station is where the trainer or the instructor sits and basically controls the training session. He runs the simulation, he can freeze the simulation, he can introduce malfunctions, scenarios, change battery limit pressures, temperatures. So you get a splash screen. So I'll click on the title. So this demo is for a single distillation column. It's a debutanizer application. So it's a column with all its peripherals. You have a water-cooled condenser, a reflux drum, reflux pumps with one running and one spare. You have a steam heated reboiler. You have a water-cooled bottoms cooler. You have a pressure controller on the reflux drum, so it's a vapor product here. You have the feed system with the feed control valve. So if you look at the top here, this is the instructor toolbar here. This is where he can do a lot of instructor functions. So let's start with the starting point for the simulation. So if I'll click on this drop down menu, I see a lot of these initial conditions. So initial condition is a starting point for the simulation. So I can start with normal operation, which is basically where the plant runs most of the time producing the product at capacity. Or you can start at a cold start initial condition. And this is basically all the equipment is shut down, pumps are stopped, valves are closed, all the equipment is de-inventory, depressurized and at ambient temperature. So this would be the starting point for a startup training exercise for the trainee operator. But normally we provide about 2 to 3 initial conditions with the simulator, a normal operation, a cold start, and maybe a hot or a warm start. But the instructor can create many initial conditions during his training session. So it's very easy to save an initial condition. So let me load my normal operation initial condition. To save an initial condition, you just go to this and type the name of the initial condition you want to save, and click on save. And now it will be available in the drop down menu of the initial conditions. So it's saved on the hard disk of this computer. To run the simulation, you would click on the run button here. So you can see that the simulation time is increasing. So that means the simulation is running. So the simulation is built to run in real time. That means any process changes that would take about an hour or so in the plant would take the same time in the simulator. So if there was a feed upset and it takes about an hour for the plant to stabilize, then it would just take the same time in the simulator. You do have a speed up function, so you can speed up the simulation. So I go to fast mode and now I run it. So now I'm running 10 times faster. This is normally used during startup, so like pressurizing and inventorying the process. That's when this speed up function is used. Otherwise, during normal training, you would run at normal speed. So the other functions that are available to the instructor are the field view. So there's an FOD button here. When he clicks on the FOD button, he can see all the field functions available to him. So you can see the cooling water valve appears. It's a manual valve in the field, which is not shown on the DCS graphic. So when he clicks on it, it appears, plus all the, if you click on a control valve, he can now operate the upstream and downstream block valves. You can operate the bypass valve. You can fully open it. So this can be used, for example, for control valve failure kind of exercise. He can stop the pump from the field. So let me go back to my normal operation here, run it. So the other feature available for the instructor is malfunctions. So I'll click on my malfunction button here, and now I can see these thunderbolt signs on all the equipment where there's a malfunction available. So for example, on the control valve, the instructor can fail open it, fail close it, stick it, put leakage or plugging. So if you fail close the valve, then I have to click apply to ensure. So the valve fails close and the flow goes to 0. So this is the situation where they can operate the bypass valve to operate the process. So basically isolate the control valve and then use the bypass valve to operate the process as close as possible to normal operation. Other failures are pumps, like all motor driven equipment, like a pump can be fail stopped. Also instruments have malfunctions, so any transmitter, flow transmitter, temperature transmitter can be fail low, fail high. So fail at its low range, high range, you can freeze it, bias it, add noise, drift. So I can fail this transmitter low, that means the flow is going to go to 0. You also have standard malfunctions for heat exchangers, so you can foul the heat exchangers. So let's go back to, I'm going to load the normal operation. The other function available to the instructor is what we call instructor variables, which allows him to change feed conditions. So you can change the feed temperature, feed pressure. So wherever you see this hand with a pen, there's an instructor variable available. So this one allows the instructor to change the feed pressure, temperature, the feed composition. He can also change the cooling water supply, pressure or temperature to simulate like cooling water failure, complete loss of cooling water or partial loss of cooling water, or the cooling water temperature going up or down. So these can be used to simulate different scenarios, different kinds of upset that might happen in the plant. You can mimic those in the simulator utilizing these malfunctions and instructor variables. In addition to this, you also have what we call as custom malfunctions, which allows you to basically introduce process-specific malfunctions like tower flooding or foaming or hydrates formation. So these are programmed in the simulator based on the customer input, and they are customized for every process. So I'm going to now switch to the DCS operator view, the emulated DCS operator. This is where the trainee operator sits and performs his function. So I'm going to start the emulated DCS operator station. So you will see that the graphic is basically the same as what we've been seeing on the instructor station. So again, you get the splash screen. However, there is no top toolbar, so he cannot run the simulation or pause it. That's an instructor function. So he basically operates from this screen as if he were in the control room and operating the real plant. So I'll go to the instructor, make sure that I'm running the simulation, and now the operator basically can open like a PID faceplate for this flow controller, change the set point, maybe decrease the flow to 35,000. So you can see the valve is closing. You can monitor it on the trend. You can put the controller in manual and reduce the valve output to say 45%. So you can see green is the controller output, red is the set point, and blue is the PV. So it went down. You can put it back in auto and give the normal set point of 35,000 and let the controller take the process back. You can monitor the process. He has a trend overview, so there'll be a trend available just like a DCS. So this is what we call a generic DCS that kind of CORYS has developed for its generic kind of simulators. But when we emulate a specific DCS like Delta V or Centum VP or Honeywell Experion, then all these faceplates and the graphics will look like those DCS graphics. So we would make these graphics look like your plant graphics. But for this demo purposes, we are using what we call a generic DCS look. So let's do a simple exercise where the instructor introduces a malfunction. So he's going to trip a pump, this running reflux pump. So he's going to turn on his malfunction view and basically fail the running pump. So as soon as he does that, we'll switch to the operator view. The operator will see that the flow, reflux flow went to 0. He sees that the pump has stopped. He can go and see the alarms. So the alarm, the low flow alarm is active, so you can acknowledge the alarm. Navigate back to the process graphic. So then he needs to diagnose the problem. So in this particular case, you can see that the pump has stopped, the running pump, and he has to start the standby pump. So since this is a field operator pump, he has to tell the field operator, in this case the instructor, to start the pump. So I'm going to switch back to my instructor view, and on the instructor I'm going to go to my field view and start the pump. If you had a separate field operator station, then it would be this function of starting the pump would be done on the field operator station. So now the pump is started. So I'm switching back to the DCS operator view, and he sees that the pump started, the flows are coming back. So you can see the PID controller is trying to take it back to its set point. So then he can monitor the process and ensure that everything is going back to normal. He can take whatever corrective action he can on his DCS screen. So now the instructor decides that, okay, this was a good exercise. Let's go back to the normal operation and run the simulation. So this time we're going to do the same malfunction, but we're going to use what a feature that is called training exercises. So let's look at, so you can develop these training exercises which are basically malfunctions or actions that can be programmed and then can be run as an exercise. They can be run by the instructor or by the trainee, and they would not know what's programmed in that exercise. So let's look at this exercise one that was prepared for this demo. I'm going to edit it. So these exercises are developed like a flow chart. They can be either programmed by like dragging and dropping these different functions on here, or you can also record them. So if I'll walk you through this particular one. So the first step in this exercise is to load a normal operation initial condition. You can change that. You'll have the same drop down menu. So you start with the normal operation initial condition, then you start the simulation, you run it for 10 seconds, and you can change that if you want. Then you introduce a pump failure, the same pump that we failed manually before, the running reflux pump. Then you start a program called TPM, an Indus Plus program. It's trainee performance monitoring. Basically, this allows the program to monitor certain variables, and those variables are programmed by the instructor or by us for the customer. And then it monitors those variables for 5 minutes here, and that's basically the time you're going to give the operator to recover from this upset of the pump failing. and then the TPM program will stop, and then the simulation will stop. So whenever this exercise is run, it's going to run for basically 5 minutes and 10 seconds for everybody. Anybody who runs this exercise, you can see it's 5 minutes, 10 seconds before the malfunction, and then 5 minutes after that. So if you want to look at what's in the TPM, I'm going to go to the TPM tab here. I'm monitoring the reflux flow, and I'm giving it a limit of 33,000 to 37,000. So the normal process value is about 35,000. So I'm saying that the reflux flow should be between 33,000 and 37,000 at all times. The level that I'm also monitoring the reflux term level, and it's at 50% normally, and I'm saying that it should be between 48 and 52 at all times. I'm also giving a weight. So whenever these variables are outside their limit, what's the weight? What's the penalty? How heavily should the operator be penalized? So for example, reflux flow is more important, so it carries a weight of 2. The level not so much, so it has a weight of 1. But you can basically have a weight of anywhere between 1 to 10. 10 being the highest penalty and 1 being the lowest. So you can program as many variables as you want for any exercise. So now I'm going to run this exercise. So I just click on run. So it's going to ask what is the instructor name for this, who's the instructor for this exercise, who's the trainee. So say it's going to be John, and do you want to compute the evaluation score? So you can either check it or uncheck it. So if you check it, then it's going to give you a score, and you'll see it in the end when it dumps a report of the exercise. So I'm going to start the exercise. So now the system loads the initial condition normal operation, then it will run for 10 seconds. So let's look at this time, 10 seconds. And then it will activate the malfunction for this pump. So the pump failed stop. Again, the flow is going to go to 0. And so now on the DCA screen, the operator is going to notice that the pump has stopped, the flow has gone to 0. So he has to basically start the standby pump. So he's going to tell the instructor to start the standby pump. So on the instructor station, I'm going to go to my FOD view and start the pump. So now you can see that the pump has started and the flow should be starting to come back. So now I'm going to go back to my instructor view. It's a 5-minute exercise, so I'm going to speed up to get to the 5 minutes because there's nothing more to do in terms of corrective action. So you'll see that at the end of 5 minutes, the system will create a report of the exercise and also give a score for the operator performance on this exercise. So we are getting close. So then the system report generates a report. You can see that. So it's the AT, the exercise is exercise 1. That's the name of the exercise. The instructor is myself, trainee is John. Duration was 5 minutes and the score was 86%. So that's pretty good. So it gives you a statistical analysis of all the variables that were being monitored by the TPM. So for example, the reflux flow crossed the low limit alarm once, which is expected because the pump stopped, and it crossed the high limit because the flow controller, the reflux flow controller wound up to 100%, and so you had a spike. How long was the excursion below the low alarm? How long was the excursion above the high alarm? How many low, and what was the total excursion time if you had multiple excursions? And the score for that particular performance of that particular variable. So similarly, it gives the same statistical analysis for the level. It also gives you a trend, and the trend you can zoom in or zoom out. You can also see the values. So this is a PDF file, but you can go and scroll and look at the values. How high was the peak? You can see the peak on the reflux was about 43,000. Similarly, you get the trend for the level. So goes up to 70% and then it's coming back down. So you have all the data that you need. It also gives you how the score has been calculated, the formula being used. So this can basically be dumped to your LMS system, your learning management system, or saved in a folder, or we can print it and save it in a binder. But it becomes basically part of the trainees training program. So now I'll briefly show you the actual engine that basically runs this thing. So this is the Indus Plus model. This is the engine that runs under the hood. So this is the model that's running in the background. So this is how we build the model. So if you look at this, there's an overview sheet, and then we create sheets for every PNID. And if I go to the process, I can navigate here to the column. So this is what the column looks like in the model builder. So here's the feed system. So here's the feed battery limit with the pressure, temperature, and the composition. So you can see got some butane, hexene, hexane. This is the flow control valve. So the valve, you have to provide the valve CV, the nominal CV at 100%, and the characteristics. So it can be a linear valve or equal percentage valve. So for the column, you have to, it's a tray by tray simulation. So this particular column has 22 trays plus the bottom drum. They're all sieve trays. We provide all the dimensions for the trays. The heat exchanger, the reboiler, it's a shell and tube, so you have to provide the heat transfer area and the heat transfer coefficients. For pumps, we have to provide the pump curve. So we have a library of all these unit operations. So if you go to the library, you can drag and drop. So if I want to create a pump, I would basically create a pump, drag and drop it, and provide the pump curve. So I can provide the pump curve. Similarly, if there was a compressor, I would provide the compressor curve. If I have a valve, I can drag and drop the valve, provide the CV and the characteristics. So this is how the model gets built for the process. So this concludes the demo of Indus Plus. If you have any questions, let us know. Thank you.
Thank you, Suhas. If you have any questions, please do not hesitate to contact me. We're happy to provide virtual lunch and learn presentations to your organization, which include a demo of our software. We will also be putting on a series of webinars this year addressing simulation needs, best practices, and case studies. So please contact me for more information if you would like to be a part of those webinars. I appreciate your time very much and enjoy the conference.
With more than 20 years' experience of research and development within eye tracking, we know that the eye holds many answers. We track, measure, and analyze human eye movements, turning sights into data and data into insights, creating a deeper understanding of human behavior, intentions, and interactions all over the world. We develop the world's most advanced eye tracking systems.
Welcome to this presentation on how head and eye tracking can provide additional clarity in research and HMI activities for energy control rooms and simulators. My name is Ulf Laffberg and I'm the sales director for Smart Eye in Sweden. I will be joined by our systems engineer Emil Rolander, who's going to perform a system demonstration after my slideshow. Emil will show you how our solution is helpful when it comes to HMI design, operator training and operator monitoring. But first, I'd like you to follow me into the world of eye tracking as we experience it here at Smart Eye. My agenda touches three main topics. I'll speak to you for about 15 minutes, during which I'll explain what an eye tracker consists of and what it produces. And I will show you a few use cases in which our systems have been deployed with our customers. And finally, I'll explain in more detail why head and eye tracking is relevant for the energy sector. After that, Emil will take over. Also for about 15 minutes, he will perform the system demonstration. So what is head and eye tracking? Our head and eye tracker measures certain biometric features in 3D. These are the head position, head orientation, eye position, gaze direction, gaze intersection with predefined areas of interest, eyelid opening, blinks, and pupil dilation. By studying eye, face, and head movements, the technology can produce data from which you can draw conclusions about alertness, attention, and focus, and thus gain insights into a person's awareness and mental state. Infrared light is used to create a reflection in the eye's cornea that can be captured on camera. Algorithms then identify the iris and pupil of each eye and weigh the two monocular feeds into a consensus gaze. The software also detects, tracks, and interprets the person's facial features and head movements. Over time, the system gets to know the face of each subject, learning more about each person while building a more detailed profile. This means that only a few features need to be visible in order to accurately determine head pose, even if the face is partially obscured. A multi-camera system also lets the software triangulate the position and orientation of the head with greater accuracy, regardless of real-world conditions. So what parts does the system consist of? In essence, the hardware is made up of IR flashes, video cameras, and a processing unit, a PC. The job of the hardware is to present video images to software algorithms. The flash and camera hardware come in different packages. Each is suitable for different situations and different environments. The most common hardware is a so-called bar tracker. It's a fixed configuration with flashes and one or two cameras. These can be used for screen-based eye tracking. Usually the tracking works on one camera only. The field of view is limited, as well as the distance between the bar and the subject and operator. Another type of eye tracker is one where the flashes and cameras are mounted on a frame that you wear head-mounted, glasses. These solutions provide an unlimited field of view, but they're not comfortable to wear over a long time, and they do not offer real-time data. The third type of hardware is single-unit flashes and single-unit cameras. Working with single units allows for flexible configuration and positioning. By placing multiple cameras, up to 8 typically, remotely around the subject, caters for a large field of view both horizontally and vertically. That means that even if the head is turned to the side or up-down like helicopter pilots or operators in a control room, the head and eyes will still be seen by cameras and the biometric data can still be captured. In addition, since remote solutions sees the whole head and face, other features like Face ID, Operator ID can be concluded and reported. The multi-camera approach is the hardware that is most suitable for control room, since it offers sufficient field of view, and the hardware is placed remotely and therefore unobtrusive to the operator. This slide is indicating a situation commonly seen in control rooms. Several screens on a desk in front of the operator and a big screen or projection on a wall further away. One single head and eye tracking system is able to track the gaze behavior on multiple screens at different distances and different angles or heights. Today, off the shelf, the head and eye tracker needed for research, development and design in the energy control room and simulator case is already available. It is the SmartEye Pro DX solution by SmartEye. The core of the solution is the tracking software running on a PC delivered with the system. Through image analysis, the algorithms produce raw 3D biometric data, as per the list mentioned earlier. The data is accessible in real time and it is time-stamped for synchronization purposes. This data can be used for two categories of investigation: gaze data analysis and biometric analysis. Gaze data is used for analysis of gaze fixation and answers the questions: what is the operator currently looking at? This in turn can be used to enhance operator training and HMI design processes. Biometric data is used for safety analysis like operator monitoring and answers questions like: is there an operator in the seat? Who is in the seat? Is the operator sleeping? Or how drowsy is the operator? Is the operator paying attention? And what is the current stress level of the operator? These analysis applications are not available off the shelf. They're typically developed within the research projects. I'd like to highlight that the SmartEye Pro system has been in use for more than 20 years. It is deployed in several different industries for both research and live production applications. Here are a few examples of industries where SmartEye Pro is deployed. Aerospace. NASA has eye trackers installed in the flight deck simulators as well as their research flight deck, where they're used to monitor pilot state and gaze behavior. Aviation. Eye trackers are used to enhance training and education of pilots in simulators. In just a few years, the aviation industry is expected to start single pilot operation and hence follow the automotive industry and install eye tracking devices in cockpits in order to track pilots' attention and drowsiness levels. This is while flying, so not in the simulator. Automotive. In the development of autonomous cars, eye tracking is a central part of making this new technology as secure as possible. Other areas where SmartEye Pro is used is clinical research, communication, medicine, neuroscience, and psychology. The following few slides show use cases from our customer base. Here an example from the University of Linköping in Sweden. The multi-camera remote eye tracker SmartEye Pro is used to analyze workload in a remote tower scenario as well as in a ship bridge scenario. We have a number of customers using our tool for research in the transportation field. Here cameras are placed in the cockpit of cars, aircrafts and respective simulators to gain further understanding of pilot and driver behavior. Also HMI design processes commonly benefit from head and eye trackers in this field. And as mentioned, research around driver attention and drowsiness is often based on these tools. A very specific application is already being deployed as we speak. It's not research, but a ready feature in standard production cars. So head and eye tracking as a consumer product. In the automotive world, it is called driver monitoring system. The technology is available to you and me now on the street. BMW is one of the OEMs offering so-called DMS as part of a safety feature package. Eye tracking cameras are installed behind the cluster or behind the speedometer and enables the car to warn the driver when drowsiness or inattention occurs. The DMS also reports on the driver ID. The ID can then be used to alter preferences based on who is driving. For example, seat and mirror positions, radio channels, HMI themes or layouts, comfort settings, etc. In aviation, several projects already aim at introducing eye tracking as a standard part of the pilot training. These systems are currently in R&D and proof of concept process or stage, but will very likely soon be deployed in pilot training facilities across the world. Head and eye trackers help the flight instructor, to determine and evaluate pilot gaze behavior in specific flight maneuvers and during problem solving and crisis management. Further down the line, we will most likely see pilot monitoring solutions built into flying aircrafts. much like what we see materialized in the automotive industry today already. Here, examples of camera positioning in the cockpit. To the left, an aircraft cockpit, and to the right, a helicopter cockpit. So now on to my last topic for the slideshow. We see several scenarios now already in use in other industries that are relevant to the energy control room scenario. The three main topics being HMI design, operator training, and operator monitoring. The physical build-up of a control room is different to what you see in a car, aircraft, or small workstation scenario. That makes the energy control room unique. The control room has more screens, larger screens, several screens at different height and distances. The operator in a control room may have to move around more compared to a pilot or driver sitting in a fixed seat. All this is a challenge for normal eye tracking solutions, but not for SmartEye Pro DX multi-camera solution. As you will see soon, with one multi-camera head and eye tracking system running just one algorithm, you can track the gaze behavior and biometric features of an operator. The robustness and flexible configuration of the SmartEye Pro DX solution allows for deployment in most control room workstations. The SmartEye Pro system delivers raw 3D data in real time. However, specific applications should be added to achieve complete systems that perform all needed analysis steps, visualizations, and report creations needed for research projects and potential production systems in the world of energy control rooms. Third-party analysis and reporting tools are available today. The iMotion software is one example, which we will show you briefly later. It is, however, reasonable to assume that new applications shall be designed and tailored for the energy sector. These could include the following features or functions. We mentioned them already. I'll just dig a little bit deeper this time. So, operator training. Gaze behavior analysis and comparisons based on pre-existing templates. Different templates for different scenarios. A scenario could be standard information collection during system monitoring. Another could be troubleshooting, or the third scenario could be crisis management. Since the analysis is based on factual behavior, the system would fall under the term evidence-based training and execute automatic rating of an operator with the purpose to improve training efficiency. This should be considered very valuable both to instructors and trainees alike. A second feature or function could be HMI design. This is similar to operator training. Also here, operator performance is analyzed. The difference is that it is not the operator that is evaluated, but the HMI system itself. By measuring how well the operator performs the design, the designer of the HMI is able to customize the setup of the complete workstation. Location of screens, what information goes onto what screen, and with what theme or size, what flow and sequence of information is best used to make it as easy as possible for the operator to perform the duties. These are some of the questions that would be answered. The eye tracker, together with adequate application, can be a very helpful tool for the designer. It's likely that the above two applications, or the above two features and functions, operator training and HMI design, would be deployed in simulators. The last example of useful applications for the energy control room is, however, intended for daily use in the live operation centers. We're talking about operator monitoring. The purpose of this application is to help understand when the operator is in a non-optimal mental state. By using head, eyelid, and pupil data, and applying drowsiness, workload, and Face ID algorithms, it's possible to create warning systems within the control room. As always, there are certainly other ideas pointing at other features and functions where eye tracking can be useful in the energy space. We're open to discuss any further topic you might have on this. I assume this is a lot of new information to some or many of you. I would therefore like to summarize the most important points again. The basic technology is here and proven in other industries. By that I mean that the most complex part technically here something that has taken us 20 years to develop. The eye tracking sensor itself, the Smart Eye Pro solution, is already available. It's here, and you can start using it immediately. We definitely think that the use of eye trackers is possible in the energy sector and also wanted in the energy sector. And last, if you use eye tracking in a control room, you do need a broad field of view, and you need something which is not disturbing the operator or interfering with your study. That's why we recommend our multi-camera unobtrusive head and eye tracker. So that summarizes my theoretical introduction. We're now moving over to the demonstration, so I'll hand it over to Emil. Thank you very much.
Hello, my name is Emil Rolander and I work as a Smart Eye engineer here at Smart Eye. I will today demonstrate a 3-camera system in this highly improvised control room, and I will focus on mainly 3 areas. One of them is HMI design, the other one is operating monitoring systems, and the third one is Smart Eye in the sense that we can use it in a training purpose. When it comes to HMI design, it's quite common to have 3 main goals of the system to be able to operate fully. Is that usually you need a wide field of view to be able to see all of these screens that we want to show. You want high accuracy to really pinpoint where am I looking on these screens, and to have the system to be non-intrusive, so blend in the environment. So a researcher might be interested in looking at gaze behavior and gaze patterns of these different screens. And depending on the information you get, you know if you're looking on one specific instrument, a warning lamp, or maybe different gauges in the environment. And while the output data gives you, you're able to suggest improvements to the system, or just to know that the HMI works because the highlighted effect of this gauge might be visible to you. As we can see in my environment here, I have a bunch of monitors, both high and low, and I even have one wall mounted behind the normal array of monitors. So this is a quite complex setup. And to be able to capture this fully, I have deployed a 3-camera Smart Eye Pro system, and I can manually mount individual cameras behind or below the monitors to capture the gaze of me as a participant. Even going above these screens to capture that one is still possible for all cameras to see me and not lose any of the data that I'm interested in. Due to the small form factor of our cameras, it's really easy for us to integrate them into any environment and to make them be, as we call, non-intrusive and adapt to any situation. For example, we have a wide array of monitors here, but if they were stacked vertically, we would adapt to that situation and instead position the camera slightly differently to blend into that situation. You could, of course, also adapt the system to any other environment, and in that sense we can increase and scale the systems to have even more cameras. We can go up to 8 cameras to adapt to almost any complex and advanced situation. In general, I would suggest that a system designed to do the HMI design studies could also just as easily be used to create something for training purposes, since they both share these common demands for high accuracy, wide field of view, and to really be able to tell where this operator is looking. And if, of course, then apply it to be able to optimize and improve exactly in what stage of a training you might to spend some extra time, and to maybe not have the time invested in spending a lot of time in expensive simulators or different environments. So just to optimize what you can do with the training system where you spend time. I want to show you how this could look inside our graphical user interface in Smart Eye Pro, to show you kind of like what we can see, and you can easily understand what the benefits of an eye tracking system in these instances could perform for you. This is the 3D world model view And this is a simplified representation of the real world, built by two-dimensional objects like screens and planes. We can populate it with as many objects as we want to and just place them freely in space wherever we like. As you can see, some of them tilt and some are a little bit more like straightforward. And of course that we designed by building this thing. You can even see the top screen here being quite much behind the other screens. And by rotating it, you can clearly see my head, which is the green ball, moving, and the red gaze vector that intersects with the different objects here. So it's a quite intuitive way of seeing my head moving, my gaze moving, with all the other objects. And this is the image view. This is of course where the real magic is happening, since this is the screen where you actually see your face and the eyes and the parts that we want to track. And I really want to show you how robust this is, so I can actually try to provoke it somehow by covering one of the cameras and really how quick the refinder is. So even if I lose tracking here really by looking at a completely other direction, you can see it's really just snaps on within like less of a second. We sometimes talk about the headbox, and that's just another way of us describing how much we can move side to side and back and forth within the environment. And I mean, with higher resolution cameras, we can achieve an even bigger headbox as we have here. And if the system isn't perfectly static, or you as an operator move a lot of times, you have the opportunity to move within this headbox. So it creates some freedom of movement, and that's great as well. And if we need to improve this even further, we can always add more cameras to go well beyond what you see here. And as I said before, we can scale it up to even 8 cameras, and that could be a full table full of equipment, and we can freely move within that space. When it comes to the aspect of the operator monitoring systems, it's usually more related to the human state of mind or the mood or mode that operator is in right now. And usually it's a lot about safety. Is the operator aware or alert to perform the task at hand? Can we at early stage detect the degradation of the alertness? Like head position or head rotation could, in combination with maybe eyelid opening or eyelid state, act as an indicator over different focus areas, but also show in which state the operator might be in. Is we are asleep or alert? And of course, like, is there even an operator behind the equipment? And the lack of an operator could maybe signal a state of something. So to be able to handle the sheer amount of data that is being collected from SmartEye Pro, it's usually a good practice to use some kind of analysis software. In this case, I've chosen iMotions because I really like how the visual representation looks and everything being collected and recorded. But it also have a lot of useful features, like aggregating different participants on top of each other for the same study, but also the fact that it's super easy to put together a specific analysis for a specific moment during that study, for example. You can see here up to the left that we have a scene camera recording everything that is happening. And as a layer on top of that recording, I can put my eye tracking data. So I, both in real time but also post-processing, can see what the operator, and I mean that's me in this case, are looking at. There is a fixation count within that view as well being shown, and along with that expanding circle that's also showing how long my fixation actually lasts within that fixation. And of course the gaze trail, which shows you the movement of my gaze pattern. Down below you have some signals I've chosen. In my case here, I've chosen pupil diameter, the distance between my head and the tracking system, but also my position in the x-axis for this system. And at the bottom you can see my consensus eyelid opening. So it's essentially, every time I blink, you can see that the number is falling down to 0, but also how open is my eyelid when I'm not blinking. At the top right you can see the world model again, almost as we saw it in SmartEye Pro, but here it's in iMotions. You can easily see the head movements and that the eye tracking remains really robust and precise. And And I mean, that's why we don't lose any data, and we can clearly see my head moving from left to right and closer to the screens and back from the screens, and yeah, it's just an easy way of seeing how everything happening, even if me as an operator falls out of the view of the scene camera. When it all comes together, we can see that the interaction between human and machine becomes more and more intricate for every passing day. In developing products, environments, and machines that are made to operate by humans, it's crucial to understand these interactions from both technical and human perspective. And that concludes my demonstration of the SmartEye Pro system in this control room environment. I would like to take the opportunity to thank you and for you to pay attention for me and my colleague as we demonstrate and talk about our system. I really hope that we have inspired some new plans or thoughts and gave you some good ideas about the future. Please, if you have any questions or anything at all, just contact us. Go into our webpage online and click around.